Hello everyone. So welcome to IIT Gate classes. So this video series is about gas dynamics topics. So today we will be seeing our next topic, that is isentropic relation. Because isentropic relations are important topic with respect to gas dynamics, or per se it is also important topic in propulsion also. So I think in today's video, so we will be seeing about how these isentropic relations are derived, and let us try to solve one or two questions. They are directly related to isentropic relations in compressible flow fields, right? So let us jump on to our topic. So I am Akshay, so your instructor for this particular course. So before moving on to isentropic relation, so I would like to quickly refresh our memories in thermodynamics, because thermodynamics is important aspect in gas dynamics. Um, so from our basics of thermodynamics, we understood that so we can have a enthalpy and internal energy relation given by this equation H is equal to E plus PV, right? So where H, E, both of them are specific properties. So like they are enthalpy per unit mass and energy per unit mass. So they are specific quantities, right? So this is H is equal to E plus P. E plus PV is a well-known relation between enthalpy and internal energy. And we also have a equation for perfect gas, that is P is equal to rho RT. So any gas which obeys this perfect gas law, they are called as a perfect gases, right? So this is a perfect gas equation. And we also have a Cp minus Cv is equal to R. This is interesting. So see here, the Cp and Cv are nothing but a specific gas constant. So like one is at constant pressure and another one is at constant volume. So that is equal to R, where R is a gas constant for a given gas. So R is usually defined as Ru by M, where Ru is a universal gas constant, M is a molecular weight, right? So we can easily show that this relation is true, because if I take a specific uh, enthalpy and internal energy equation, I have H is equal to E plus PV, or so we know that rho is nothing but 1 by specific volume. So I can easily write this one, PV is equal to RT. That is also true. So H is nothing but CPT, and internal energy is nothing but CVT. So if I use that idea, so I can easily write that one, this equation, as CPT is equal to CVT plus PV is nothing but RT. So, and if I take T common in this equation, so that becomes Cp minus Cv times T is equal to R times T, right? So if I cancel out T on both the sides, so that leaves me a Cp minus Cv is equal to R. So this equation is perfectly valid even for calorically perfect gas, where Cp and Cv are functions of temperatures, right? Yeah, so that is one equation we have. And we also have a ratio between the specific heats, sometimes called as ratio of specific heat. So that is denoted by gamma. So that is a specific heat ratio. So this is our another equation. So from here we can show that, so we can write Cp and Cv in terms of gamma and R. So that is uh, that we can show that, like Cp can be written as gamma R divided by gamma minus 1, whereas Cv can be written as R divided by gamma minus 1. That we can easily show, right? So now we have laws of thermodynamics. So that is first law of thermodynamics tells us conservation of energy. That means like energy can neither be created or nor be destroyed. It can be transferred from one form to another form. That is the basis for uh, first law of thermodynamics. So that says us delta Q plus delta W is equal to dE. So here we have to pay attention to the notations we are using over here. dE, that is finite difference. So I can easily write dE is equal to E2 minus E1 form, because internal energy is a point function. So I can easily show that if the process is taking place from point 1 to point 2 or state 1 to state 2. So it all matters is like what changes occurred between state 1 to state 2. So I can easily write E2 minus E1, whereas work as well as heat. So Q is denoted as a heat per unit mass, where so heat transfer per unit mass, where W is work transfer per unit mass. So these two are not a point functions, they are the path functions. So they depend on the path through which a process is taking place. So that is why I cannot write in this form like dq is equal to q2 minus q1. That is not correct. So I have to integrate over the path, and I have to get the exact value of the path, the heat transfer or the work done. So that is why we usually denote it using delta q and delta w. So that is notation we use it for a path function variables, right? So then we have a second law of thermodynamics. Why in the first place we need a second law of thermodynamics? Because the first law of thermodynamics only guarantee you the conservation of energy, but it doesn't speak about the direction in which the process has to take place. Like for say, take an example, you are placing a cold ice cube on a hot plate. So according to first law, you can say that the ice is getting colder and colder, and the plate is getting hotter and hotter. That is possible with the way if I express in the first law. So that doesn't violate the conservation of energy. But the problem is, we know from our understanding, and nature doesn't allow us to say that the ice is getting colder and colder and plate is getting hotter and hotter. It is not the scenario. The ice has to melt down and the plate has to cool down. So because of the to attain the balance between the temperature in the ice and to the plate, right? So that is why the second law of thermodynamics says that the process will takes place such that the entropy of a system is going to increase. So that is important direction, so in which the process has to take place. So the second law of thermodynamics that brings in that constraint in which direction the process has to take place. So the second law of thermodynamics has a various definitions. So altogether it's called as a second law of thermodynamics. There is a Kelvin-Planck statement, there is a Clausius inequality statement. So there is different statements, but in a nutshell, so I can say that, so second law of thermodynamics relates the direction of the process. So that is related with the entropy, the change in entropy in the system during the process. So here you see, I have a equation form that is ds is equal to delta q reversibility is divided by t. This is how the entropy change in the system is defined during the process. And if I have to give the more precise definition for a second law, so that is this equation, right? So where I have a ds irreversibility. So this is nothing but an entropic change which occurs due to irreversibilities in the system. So that can be like due to a friction or some kind of irreversibilities can arise, like thermal diffusivity or viscosity. So these are the some variables. They are going to induce irreversibilities in the system. So my second law of thermodynamics can be written in terms of ds is equal to delta q by t plus ds irreversibilities. And the irreversibilities which is in the system, which are always going to increase the entropy. So that means ds irreversibilities can be greater than or equal to 0. They cannot be less than 0. So that is one more constraint we have. So it is equal to 0 when there is no irreversibilities which is present in the system. So this is greater than 0 whenever we have a irreversibilities within the system, right? So for isentropic relation, so that is the topic of our interest today. For that one, we will be considering a process which is adiabatic as well as reversible. So that means we are not going to treat irreversibilities in the system. So we are assuming there is no irreversibilities which is present within the system. We are also going to take an assumption that heat transfer within the from the system to boundary the system to surrounding is not present, or even the surrounding to system, it is not present. There is no heat transfer within the process. So the process is taking place with no heat transfer. That is the idea of adiabatic process, right? So that leaves us ds is greater than or equal to 0, because there can be reversibilities for adiabatic irreversibilities in our adiabatic process. So when we consider it's an isentropic process, then only we bring in that constraint of ds is equal to 0. There is no change in entropy, right? So from the process, what we have, that is from the second law, ds is equal to delta q divided by t. So we are not treating any irreversibilities as of now. So I can easily show that that is nothing but delta q is nothing but t times ds. So these TDS relations are very important. Also, we have from our first law of thermodynamics, that is delta q plus delta w, which is equal to dE, right? So I am going to replace this one as TDS plus delta w. I'm writing as it is now, dE. And I can also show that the delta W is nothing but the flow work. So that is nothing but delta W is nothing but minus PdV. So I can write like this for the flow process. So this leaves us a TDS relation, that is TDS is equal to dE plus PdV. So this is one of the important equations I'm interested in, right? So this is one of the TDS relation. So another TDS relation also can be formed. So that is through I have H is equal to E plus PV, right? So I can write in a differential form, that is DH is equal to DE plus PdV plus VdP, right? So this is nothing but DE plus PdV. DE plus PdV is nothing but TDS, right? So that we have seen. So from equation 1 over here. So I can write DH is equal to TDS plus VdP, right? So now what I can do? So I can write for a TDS. So TDS is equal to DH minus VdP. So these two are very important TDS relations, so that we are going to use to derive the isentropic relation, right? So now we will head back to our isentropic relations. So from a TDS relation, right? So we have a first TDS relation, that is relating TDS is equal to dE plus PdV, right? So I also have the equation of state that says that PV is equal to RT, right? So we will keep this in mind. So now I can write it for ds is equal to, what is dE? If E is equal to Cv times T, so then means dE is equal to Cv times dt, taking a Cv to be calorically perfect gas. So or yeah, calorically perfect gas. So that gives me dE is equal to Cv times dt. So I can write this equation Cv dt. So I am dividing T throughout the equation, so that becomes dt by T plus P by T times dV. What is P by T? So if PV is equal to RT, that means P by T is equal to R by V, right? So I can write that part over here. So that becomes ds is equal to cv times dt by t plus r times dv by v. Right. So now this is a very straightforward differential equation. So I can get a solution for this differential equation if I integrate from state 1 to 2. Let's integrate from state 1 to 2. So my equation looks like S2 minus S1 is equal to, if Cv is constant for calorically perfect gas, Cv times ln of T2 by T1 plus R times ln of V2 by V1, right? So this is TDS relation, which is integrated from state 1 to 2. That's the process is taking place from 1 to 2. So this is how it looks like, right? So I will call it as equation 3. So similarly, I have another TDS relation, that is TDS is equal to, in terms of enthalpy, dH minus VdP. So again here, I have H is equal to Cp times T. So that means dH is nothing but Cp times dt. So I can replace that one and dividing the entire equation by temperature T. So that becomes Cp times dt by T minus V by T times dP. What is V by T? So if I look at PV is equal to RT, V by T is nothing but R by P. So I can write this equation in terms of Cp times dt by T minus R by R times dP by P. So if I integrate from state 1 to 2, so that becomes S2 minus S1 is equal to Cp is constant times ln of T2 by T1 minus R times ln of P2 by P1. So I will call this equation to be 4. So from these two relations are important when I go forward and show the isentropic relations. So what is an isentropic relation? The isentropic process is in one which there is no entropy change. That means S2 minus S1 is equal to 0. If S2 minus S1 is equal to 0, so from equation 3, I had, so if I keep left hand side 0, that is S2 minus S1 is equal to 0. So that means 0 is equal to Cv times ln of T2 by T1 plus R times ln of V2 by V1, right? So if I rearrange this one, this becomes ln of T2 by T1 also minus Cv by R times ln of T2 by T1 is equal to ln of V2 by V1, right? So I can write like this using the logarithmic rules, that is A ln B is equal to ln B to the power of A. So that becomes, so if I equate both the terms within the logarithm, so that is nothing but T2 by T1 to the power of minus Cv by R, which is also equal to V2 by V1. So, or what is Cv by R? So I have Cv is equal to R divided by gamma minus 1, or Cv by R is nothing but 1 divided by gamma minus 1. So that becomes T2 by T1 to the power of minus 1 divided by gamma minus 1 equal to V2 by V1. Or if I write in terms of T2 by T1, so that is nothing but T2 by T1 is equal to V2 by V1 to the power of gamma minus 1, that is reciprocal. So minus gamma minus 1. So that becomes, I can also write this one in terms of V1 by V2 to the power of gamma minus 1. So that is also fine, right? So this is one relation. So when I take it from equation number, I will call it as equation number 5. So now I have another relation, TDS relation, that gives me S2 minus S1 that is equal to 0. That is also equal to Cp times ln of, T2 by T1 minus R times ln of P2 by P1. So from equation number 4. So from here, I can again rearrange this one. That becomes Cp divided by R times ln of T2 by T1, which is also equal to ln of P2 by P1. Right? So if I again use the same logarithmic rules and equate the terms within the logarithm, so that becomes T2 by T1 to the power of Cp by R equal to P2 by P1. Or else I can show that if Cp is equal to gamma R divided by gamma minus 1, that means Cp by R is equal to gamma divided by gamma minus 1. So I can use that one over here. So that becomes a T2 by T1 to the power of gamma divided by gamma minus 1 is equal to P2 by P1. Right? Or else, if I want to write in terms of T2 by T1, just like in the other case, that is T2 by T1 is equal to P2 by P1 to the power of gamma minus 1 by gamma. Right? I will call this as equation 6. So now I can easily show that there are two equations, 5 and 6, that relates T2 by T1 is equal to, one is in a specific volume ratio, other one is pressure ratio. So the other relation we had is T2 by T1 is equal to V1 by V2 to the power of gamma minus 1, or I know that rho is equal to 1 by V. So I can also write this one in terms of T2 by T1 is equal to rho 2 by rho 1 to the power of gamma minus 1. This is also equal to P2 by P1 to the power of gamma minus 1 by gamma. So this is the well-known isentropic relation. This is important relation between the thermodynamic variables within the process. So I can relate thermodynamic variables using these relations if the flow is going through a isentropic process, right? So now we will we will see some of the questions which is asked in previous year gates regarding the isentropic relation. See, the first question we are going to address here is the relations between a pressure P, velocity V for a steady isentropic flow at 2 points along a streamline is, with a C being a constant, right? So the question is straightforward. So they are given four four answers. So we have to choose the right one. So I have a streamline. I have a point 1 and 2, and that the flow is going through an isentropic process along a streamline. So here they are given pressure P and V, that is P1 comma V1, and here I have P2 comma V2, right? So they are asking what is the relation between a P1 V1 P2 V2 in if the flow is isentropic. So how can we show that the relation between these two? So the best choice here is to start off with energy equation. So for the energy equation for a compressible flows, we have with no viscosity. So that means like no body forces and no viscous effects. So that energy equation somewhat looks like and steady. So the question is already given, steady isentropic flow. So that is why H1 plus V1 square by 2 is equal to H2 plus V2 square by 2, right? So this is isentropic energy equation for a steady flow. So it is even true for adiabatic. So it's a general energy equation with no body forces and no viscosity effect. So this is an inviscid compressible energy equation in a steady flow, right? So that is and flow, if the flow is adiabatic, that has to be taken care when we write this energy equation. So now I can write H is equal to CPT if it is the gas is assumed to be calorically perfect. So I can write CPT1 minus CPT2 equal to V2 square by 2 minus V1 square by 2. Or I can also write in the other way, that is V1 square by 2 minus V2 square by 2 equal to CPT2 minus CPT1, right? So because I want V1 square by 2 and V2 square by 2 form, that is given in all the options. So that leaves me, if I take CP constant, that leaves me T2 minus T1, right? So now this left hand side, whatever over here in this equation, that is nothing but the right hand side of the given option. So the right hand side is fixed. So what we have now, so the right hand side is fixed, that is V1 square by 2 minus V2 square by 2. So that is nothing but CP times T2 minus T1, right? So if I take a T1 common or a T2 common in this equation, so that becomes CPT2 equal to 1 minus T1 by T2, which is equal to RHS. And what is this T1 by T2? So this is the flow is isentropic. So I can use the isentropic relation between the 2 points in the streamline. So that is nothing but I can write T1 by T2 is equal to, so I want it in terms of pressure. So I'm converting it in terms of pressure using the isentropic relation, that is gamma minus 1 by gamma form. So that is nothing but, and what is CPT, right? So Cp is nothing but gamma R divided by gamma minus 1. So this is nothing but gamma R T2 divided by gamma minus 1 times 1 minus P1 by P2 to the power of gamma minus 1 by gamma is equal to RHS, right? So what is RT? So I know PV is equal to RT, or I can write in the other way, P is equal to rho RT. The both are same. So RT is nothing but PV. So R nothing but P by rho. So I can write gamma by gamma minus 1 times P by rho is equal to, so if I take the LCM of this one, so that becomes P2 to the power of gamma minus 1 by gamma minus P1 to the power of gamma minus 1 by gamma whole divided by P2 to the power of gamma minus 1 by gamma. So this is T2. So this is nothing but P2 by rho 2, right? So equal to RHS. So all we have to do is now the proper LCMs. So what is this one? P2 power 1 and P2 power gamma minus 1 by gamma. So that becomes P2 to the power of 1 minus gamma minus 1 by gamma. So if I take the LCM over that one, that gives me P2 to the power of gamma minus gamma, gamma gets cancels plus 1. So that is 1 by gamma whole divided by rho 2. So this is what we are left with. And we have for an adiabatic flow. So isentropic flow is nothing but adiabatic as well as reversible. So that is why P by rho to the power of gamma is equal to constant, right? Or if I raise the power by 1 by gamma, what happens? That becomes P to the power of 1 by gamma divided by rho is equal to constant. So constant to the power of 1 by gamma, again a constant. So I am not writing, I am not showing that step. So we know P by rho to the power of 1 by gamma is equal to a constant. So I can replace this equation like gamma by gamma minus 1 times P2 to the power of 1 by gamma by rho 2 times whatever I have here, P2 to the power of gamma minus 1 by gamma minus P1 to the power of gamma minus 1 by gamma, which is equal to RHS. RHS is nothing but the velocities. So now this one is constant. We have seen that. So if this is a constant, so that means gamma by and gamma minus 1, that is again a constant. So this entire term is a constant. So I can write C times P2 to the power of gamma minus 1 by gamma minus P1 to the power of gamma minus 1 by gamma, which is equal to V1 square divided by 2 minus V2 square divided by 2. So that is the uh, um, relation between pressure and velocity. So now if I go back and check which option should be correct, so that is option C, right? So as a algebraic simplifications, it looks a bit lengthier, but what you can do is like once you arrive at this particular relation, you can decide which of the option is correct. Like in the next step, like all you have to going to show is like the term which is multiplying to this one is a constant. That is what you are proving essentially. But you got the required form, like the exponent. The exponent is what varying in all the options, right? Once gamma by gamma minus one, sometimes gamma minus one by gamma and gamma minus. This exponents is what making confusion. So once you get that exponent form, you can decide which of these options are correct. That is the trick to answer this question. But in my view, it is better to show the complete steps and convince yourself. Indeed, that is the correct option. So that is the better way to answer this, right? Okay. So now we will check the next question. That is ask for a rocket motor which has a chamber pressure of 100 bar and a chamber temperature of 3000 Kelvin. The ambient pressure is 1 bar. And assume that the flow in the nozzle is isentropic and optimally expanded, the exit static temperature in Kelvin is. So they are given a rocket chamber, and from there the nozzle is attached to the chamber and the flow is expanding through nozzle to an atmosphere at PE is equal to 1 bar. And within the chamber I have P naught. So I know at the chamber there is no velocity, so that the pressure within the chamber is a stagnation condition, so that is 100 bar. And I have a temperature in the stagnation chamber, that is T naught is equal to 3000 Kelvin, right? So these are the information given. They are asking what is TE, the exit temperature is what, right? So again, this is fine. So if I take a streamline which is passing through a nozzle, so from state 1 to state 2, that is state 1 is at the combustion uh, combustion chamber of the nozzle, so this rocket. So there state 1 is there, the state 2 is nothing but the exit. So if I can use the isentropic relation on this streamline which is passing through the nozzle, right? So this I can easily write that P naught by PE is equal to T naught by TE to the power of gamma by gamma minus 1. I am just using the isentropic relation between the chamber to exit, right? So now they are asking me to calculate TE. So I can write TE is equal to T naught times TE divided by P naught to the power of gamma minus 1 by gamma. So in the question, the gamma is not given. So we can assume it for gamma is equal to 1.4 for this particular question. Though that is a missing part in the question, because usually in the rocket and, nozzles or expansion in the gases in the rocket nozzles, the gases will have a different compositions than the air composition. 1.4 is for air, but in the question they were actually mentioned a CP as 1000 joules per kg Kelvin. So that is that one I have not shown here, but for close to CP is equal to 1000 joules per kg Kelvin, the gamma becomes 1.4 for air. So that is why I am choosing gamma to be 1.4. But remember that value is usually given in your gate scenarios, the value of gamma, or at least they will give a way to calculate gamma, right? Okay. So now I am using just the given information. So that is TE, that is equal to 3000 times PE is 1 divided by 100. So both of them have the same unit, so I don't have to convert here. It's a ratio. And 0.4 divided by 1.4. So if I do that one, I should get 805 Kelvin. So that 805 Kelvin is option A. All right. So I think this is the last question I wanted to discuss on this particular class. So whatever the question which is being asked using isentropic relation, they will be straightforward, at least in a way that, like, if you understood the idea of how these relations have been derived, so you can easily answer those questions. So that ends our discussion on isentropic relation. So thank you for listening to this class. And for more information, you can contact us at iitiansgateclasses. And the new batch for GATE 2023, the crash course batch, is started from November 1st. So you guys can welcome to join. Okay. Thank you, one and all.